Okay, now let's look at this example here. Okay, in general, let's assume this is non-zero. Let me put it I0. Okay? So we have a linear system equation. L times I plus R times I equals V. Okay, you know that. So what is the solution for the current? So here we have an input. The input is Vs. Okay, that's the control voltage. And then the output is the current. It's a simple RL circuit. And then we put this system S. Now initial condition, let's assume is I sub 0. Suppose it is non-zero. Now this notation, 0 sub minus, that means which is smaller than 0 but very, very close to 0. Okay, suppose I have for current. This is T, and this is I of T, and this is 0. Then 0 sub minus, that would be the time next to the 0, but very close to 0. Okay? So initially, suppose we have a non-zero current, I sub 0. Initially, suppose that is the case. So how do we solve this equation? Now there are numerous ways to do that. Last time we used the what? Cofacting, I'm sorry, the multiplying factor, right? We multiply the equation by a second. Okay, let's see to the R over L over R. This one we are not going to use that method again. So this applies a different method. This applies the Laplace transform we have just learned. Okay, so let's take Laplace transform over the entire equation. Li dot plus R times I equals V. Okay, so we have L. L is the constant. L is the constant. L is both are constants. L is the inductance are the resistance. So both are constants. Supposed to be. Okay, they are the inductance and the resistance of the circuit. So L times the Laplace transform of I plus R times the Laplace transform of I equals the Laplace transform of V. Okay? Now since L and R are constant, so we can take that out of the Laplace transform. It's a property because Laplace transform is a linear operator. Okay, and sorry, this should be I dot. This is I dot. Oops. Okay, let me keep the differentiation here. Sorry about this. So that I will not confuse you. Okay. Laplace transform of the differentiation of the curve. Okay, so can anyone tell me? Please look at the table. What is the Laplace transform? Okay, let me look large. What is the Laplace transform? Of the differentiation of a function. What's that? Open your note. Come on. Open your note. Or open your cell phone. Whatever. You can find a solution. In the lecture notes, yeah. We have a property, but we did not mention that specifically. That is something I want you to prove. Okay, let's take a look here. Okay, last time we just went through that very quickly. Okay? The Laplace transform of the derivative of a function df over dt, Laplace transform of df over dt is equal to s times the Laplace transform of f, which is defined as capital F of s, and then minus the initial value of the function. Okay, because here we consider one-sided Laplace transform. So the initial time is 0, or 0 sup minus. It will be to the left of the 0 initial time. I need you to memorize this, burn that in your memory. So this is equal to s times the Laplace transform of f of t, and then minus f0 sup minus. Okay, some of the books simply use f of 0, that's fine. That's also fine. But in case there is an impulse at 0, then it's better to use this location here. Use this initial condition. Okay? So we call this f of s. So we are going to implement this result. Okay? So we have L times S times I of S. And then minus the initial value. Okay? So for convenience, let's define I of S. Define I of S is the Laplace transform of L of t. Okay? Define. So the Laplace transform of the I over dt is equal to S times L of S minus the initial value at 0 or 0 sup minus. Okay? Now, like I told you before, if there's no initial condition or 0 initial condition, the Laplace transform of the differentiation of a function is simply equal to S times f of s. Okay, this is 0. So in many of the fields, or especially for the electrical engineering, we use S to denote differentiation. Remember that? So S is derivative or differentiation in S domain. That corresponds to the d over dt in the time domain. Okay? Sorry. Let me switch to this is in the S domain, and this is in the time domain. Okay, you have to keep that in your memory. And then the remaining terms are straightforward. Okay, and let me call this small v. Let me change the notation to small v sub s. So the capital V sub s is the Laplace transform of the small v sub s of t. So after the Laplace transform, this is the capital V of s of s. The Laplace transform of this voltage source. Okay, so what we have here is Ls plus times Ls. Okay, that's the addition terms, right? And then bring the integrator to the right hand side, now equals to Vs, and then plus L times L times the L times the Laplace transform of the initial value. Okay? So out of this, the Laplace transform of the curve, it is simply equal to 1 over S plus R times V of S. And then plus L over Ls plus R times the Laplace transform of the initial value. Okay, let me ask you a quick question. What is the Laplace transform of the initial value? What is this? Come on, think about this. By definition, what is that? Right? If you integrate the initial value, it is just a constant. Am I right? Okay. And then, can I write it in this way? That a constant times 1 times e to the negative t. This constant has nothing to do with the integration, so it can be moved out of the integration. And we put the number 1 there. Okay, could you tell me what is the Laplace transform of the number 1? Come on, check out your lecture notes or check out your notes. Come on, open your lecture note. Come on. It's in the paper. Okay? Open your lecture note. I mean, it's in my lecture. Okay? In my lecture note. Did you find something? What is the Laplace transform of the constant 1? What's that? Come on, can you write for me? Come on. 1 or 1 over x. Okay, I think you are tired like me. That's 1 over x. That's the Laplace transform of unit step function. Okay, so that is equal to initial value times 1 over x. Okay, so the help us in reading this. All right, now, if okay, so this is the general solution, but inertial manner. It is inertial manner. Okay? So if I want to determine the solution in time domain, I take the inverse Laplace transform. I take the inverse Laplace transform over the entire equation. So the left-hand side is simply the curve, but in time domain now. And the right-hand side, I have to take the inverse Laplace transform over the entire function. And this one. Okay? Now, these are just notation. It doesn't mean much to you. Doesn't mean much to you. Okay, let's consider some special cases. Now, case number 1. Okay, this is something we are much more interested in. Now, if the initial value is 0, okay, then we have LS equals to ES over S plus 1. Then we can divide that equation by ES. Now, in the field of control, we have a particular name, specific name for this. We call this the transfer function. So this is the Laplace transform of output over the Laplace transform of the input. Okay, by definition. So what we have is a very simple block diagram to represent the system. The input now is the voltage source, Vs. The output is the current on the circuit. And the transfer function is simply 1 over the rest of the okay? So this is the transfer function. In the field of control, okay, in control engineering, we use this block diagram to represent the circuit. Or to use this kind of block diagram to represent a very complicated system. We can interconnect many different small subsystems. And what is the solution if we follow the impulse? What about the impulse? Okay, let's assume the system input is the impulse function, u(t). Okay, so in this case, Vs is in unit t, right? This is equal to unit t. Then if Vs of S, the Laplace transform is simply the Laplace transform of the unit function. So what is the Laplace transform of the unit function? Come on, can anyone tell me? 1. Good. You need to memorize this. Put this into your memory. Okay? So in this case, then the output I of S is simply the transfer function G of S times the Laplace transform of the input. So we have 1 over Ls over R, Ls plus us. Okay? Then for simplicity, we can normalize the coefficient, so divided by L. So we have L times S plus R over L. So we go to 1 over L and S plus R over L. Right? So the current in the type of map is simply the inverse of Laplace transform of Ls. Okay, you know there is a scalar 1 over L. Okay, now can anyone tell me what is the inverse Laplace transform of 1 over L, 1 over R, 1 over S plus R over L? What's this? That's equal to e to the what? Come on, this is one of the most important functions I need you to memorize. What is the inverse Laplace transform of this thing? Sorry. Okay, good. Okay, and this is for t greater than or equal to 0. Okay? So if you sketch the time response in a time domain, it will be an exponentially decay function. This is in time domain. This is in S domain. Now look at the I of S in S domain again. Okay, you need to use this over here. What is the pole of the transfer function? Okay, so G of S is equal to so the pole is equal to, let me put it, say ST or P, P is equal to 1. What is the pole? We solve the equation. Okay, so S plus R over L equals 0. In any case, S is equal to negative R over L, right? And this is the pole. What is pole? Replace SIP. So the pole is negative R over L. So in the S plan, there is a complex frequency domain. It's the location of the pole is on the negative real axis. And the time response is this guy. It's this one. Why I want to bring this again, because that tells us how do we determine the stability of a linear system. we can determine the stability of a linear system in S domain directly. Okay? From this figure, from this response, time response, you can see that as t approaches infinity or a big number, the limit of LT approaches to where? Approaches where? When t approaches infinity, LT approaches to where? Come on. Aerospace engineer. I know, so we have come on, tell me. When t approaches infinity, what is our t? 1? Wrong answer. T approaches infinity. Okay. For example, negative 100. Okay, this is the constant, right? This is going to be 1. 1 again? 0. Right. A very teeny tiny small number. Yes. That would be a very, very small number, 0. When t approaches infinity. So this kind of response, we call the system is stable. When t becomes very big, you let the system go for quite a long time. Eventually, the system the system response approaches 0. So this kind of system, we call that stable system. We use the word stable system. Okay? Now, we can extend the concept to higher degree system, to higher order system or higher degree polynomial. And they will have the similar denominator or similar conclusion. So for all the poles of the system, okay, so here's a quick remark. I don't want to go through the mathematical proof, okay, it's quite a long time, but we all understand. So if all the poles of geometry are on the, let me call it open left half plane. Open left half plane. Okay, I will explain this to you again. The system is stable. Stable. What do I mean by that? Open left half plane. If the poles has, okay, let me use the space here. Okay. If the pole pi, say, equals to, say, sigma plus j omega. Okay? Sigma I, omega I. Okay, I can be 1, 2, 3, depending on the order of the system. Left. Then the pole pi equals sigma I plus j times omega I. So suppose the pole is here. Okay, I think I mentioned this last time, but let me give you a much more specific expression. So if I have a pole, okay, this is Pi, the real part is 4, okay, Pi. The real part is sigma I, okay. The imaginary part is omega I. So the Pi can be written as sigma I plus J times omega I, okay. If the sigma I is smaller than 0, to the left of the j omega axis. This is j omega axis. Sometimes we use the word j omega axis to represent the imaginary axis. And Pi is on the open in the open left half plane or half S plane. Then this is a stable pole. Okay, then the system is stable. We call this stable pole. And last time I showed you a figure, okay, for different locations of the pole, the time response will be different. Okay, now let me show you the time response of different locations of the pole again. Okay, so you can see that if the poles of the transfer function are in the open left half plane, those are the locations of the poles. And one, the triangle left plane. Their response will be something like this. Okay, there's a imaginary part, then it's going to oscillate. The time response is going to oscillate. Okay, this is multiplied by sine or cosine, either depending on the definition of the initial value. Okay, but either one, okay, or on the negative real axis, you can see that as t approaches a big number or infinity, the time response eventually approaches what? 0. Okay? And this kind of response is called stable response. The system will be called stable system. Stable system. Alternatively, if there's a pole located on the right half plane, and these are the right half plane pole, you can see that it's going to oscillate with bigger and bigger amplitude. Okay, and this is going to grow without bound. So this kind of response is called unstable response, and the corresponding system will be called unstable system. Now, be careful here. If a transfer function G of S, say, has 100 poles, suppose 100 poles, 99 of them are stable, but one of them is unstable. Let me ask you, is the system stable or unstable? Okay, 99 of the poles are stable poles. Okay, but only one of the pole is unstable. Then the transfer function G of S is stable or not? Is stable or unstable? Okay, let me repeat that again. Okay, suppose I have a system, GLS, which is 99 stable poles. Means 99 poles are in the open left-out plane. Okay, but only one is here on the positive real axis. Then, how do I categorize the system GLS? Is it stable or is it not stable? Is it stable or unstable? Let me say that. Stable or unstable? One of you are shaking the head. Give me your reason, please.
For the whole system to be uniform, then I would just try to fix that error.
It's not the error, okay? We don't take the average. We have to consider what I just told you. When time goes to infinity, what will happen? 99 of them goes to 0, right? 99 of them, the 99 poles, their corresponding function goes to 0. You know that, we know that. Okay? But one of them is unstable. One is unstable. One unstable pole. Now this unstable pole, what happens to the corresponding function? It's going to grow without bound eventually. Okay? So what does that tell us? What does that tell us? Means, even so, the system is still unstable. Because if you observe the transfer function, if you observe the system output, why? This output, if we consider linear system, right? It's a combination, linear combination of those small output corresponding to the poles. Even though 99 are stable, eventually that approaches 0. But the last one, this guy is a bad guy. It will grow without bound. It's going to grow without bound. Eventually approaches infinity. So if you look at the output, you will see, wow, the output eventually also grows without bound. So the system is still unstable. Okay? We don't take average. We don't take average. So long as one of them is a bad, let me say, maybe it's not wrong to say that. So long as one of them is unstable, is an unstable pole, then the system is unstable. Period. Okay? Alright, so again, let me remind you, this is an important figure in the chart. Burn this in your memory. If the poles are in the left half plane, the corresponding output is a stable function. Okay, either on the negative axis, the corresponding response is exponentially decay. On the left half plane, but with complex part, with imaginary part, it will oscillate, and eventually the amplitude will become smaller, and approaches 0 as well. So they all die off eventually. So these are the stable behavior, stable output, stable response. And on the right half plane, eventually they will grow without bound. Okay? So these are the unstable response. The corresponding system is unstable. Okay, all right. So hopefully that will give you a very good impression. to the initial value. If we do that initial value, then we have to take the inverse Laplace transform. All right. Maybe we'll see that later. That's fine. Okay, sorry. Okay. Okay, I think this one is easy, so I'm going to ask you to read it also. Okay. All right, another example. Now, this example is talking about the time shift. Okay, so so let me copy this. Okay, so just consider the so here we have a function which is a combination of two functions. Okay, this is this u of t. Okay, so there's no big deal here. But if you try to sketch, it's going to come. It is going to come. Okay. So how do I take the Laplace transform of x1 of t in this case? So if I take the Laplace transform equal to whatever. So let's take the Laplace transform, see what happens. Now, since the Laplace transform is a linear operator, so I can split the two terms. Okay, give me 1 second. Okay, write one more line here. Now, for the Laplace transform we are taking, we are using the one-sided Laplace transform, which means this. If we define a function by, okay, unit step. Okay, unit step. Let's define as u of t, the function value equals what? When the t is bigger than or equals to 0. U of t is 0, follows, right? So actually, this u of t does not have any influence on the integration. So we can simply throw it away. Okay? Because we are using one-sided Laplace transform. We start from 0. So we don't need to carry that anymore. So this is equal to the Laplace transform of sine of 2 pi t. But what about the second term here? The second term, sine of 2 pi t minus 0.5, and then multiplied by the unit step function with the delay, 0.5 second delay. So how do I take care of the delay when taking the Laplace transform? Okay? Alright, so let me stop here for 10 minutes and then come back after the break, okay? Think about this. Maybe you have already learned Laplace transform when the function involves a time delay. How do we take care of that? And I'm going to assign the homework for this week. I need you to prove the following properties, including this one, the time shift. Okay, please prove the following properties: time shifting, derivative, integral, initial value theorem, and the final value theorem. So please prove the following properties. First one, time shift. Second one, derivative. Third one, integral. And then initial value theorem. And final value theorem. Okay, you can find the answer from many different books. Now we need this. For this problem, we need time shifting. Okay, this is also very important. So let's see what does that tell us. What does that tell us? It says that if I have a shift in a time domain, okay, say alpha second shift in a time domain. Okay, also have to multiply the unit step with shift. Okay? Then the Laplace transform is the Laplace transform of f of t times e to the negative alpha s. So this is the time shift in the S domain. There we go. So suppose I have an f of t in the time domain initially. Okay, suppose this is my f of t. But now I delay, I shift. Okay, so maybe I should be here, supposedly. So this is f of t minus half times u of t minus half. So I shift the function to the right. Shift the function f of t to the right, say alpha second. First of alpha. Then when I take the alpha transform, so that will multiply by e to the negative s. Then in the time domain, this is equal to okay? I want you to prove this. So we call this e to the alpha, negative alpha is the delay operator. This is the delay operator. E to the negative alpha is that's the delay operator. Okay? I need you to prove it. So I'm going to use this property directly. So now I have e to the negative 0.1 s times the Laplace transform of the original function without delay. Okay? So this is the purpose of this example. How do we deal with the delay? We have to multiply the Laplace transform of the function by the delay operator, e to the negative 0.5s. Okay? And then we can correct the terms. All right, so now I need you to tell me what is the Laplace transform of sine 2pi times p? Well, this squared. 2pi squared. 2pi. Okay, this comes from where? If you take the Laplace transform of sine omega t, that's equal to omega over h squared plus omega squared, right? Okay? So again, I need you to burn this into your memory. These are the important functions you have to remember, you have to memorize. Okay? So that's it. So for this example. And the second part of the example, I think we can read it ourselves. Second part. All right, any questions up to this moment? Okay, all right. Okay, let's consider a very important topic, but I think I mentioned that very briefly, but let's go to the topic a little bit detailed again. This is the second one. 3.6, okay. Transfer function. Okay, I mentioned that in the last hour, but let me go through that again. Remember in the beginning of the chapter, if I have an input XLT to the linear system HLT, the output is 1LT. Then the output is a convolution of the input and the impulse response of the system, right? Okay? The general expression will be this one. But as we have discussed, if we have a complicated or interconnected system, suppose we have some series connections system, H1, H2, and H3. To determine the output from the input is very complicated. Not mention that if we have a feedback, then convolution becomes an implicit expression. It's almost impossible to solve, okay? And then we have to find some other method to overcome this problem. So we can prove that if I take the Laplace transform of the RLT, that's equal to the Laplace transform of the convolution of the input and maybe for that GLT, just for notational convenience next later on. Okay, and then we can prove that this is equal to the Laplace transform of the input signal XLT times the Laplace transform of the impulse response of the system. This is very crucial. It is a very important result, even though it's very simple. It simplifies lots of things when we are dealing with control systems. And we call this F of S times G of S. Okay, where this is well. Is the Laplace transform of T, and the G of S, that is the Laplace transform of the impulse response, G of T. So symbolically, this kind of block diagram many times. Symmetrically, in a time domain, the input system is x of t. The output is y of t. Okay. Right? That's u of t in a time domain. But in the next domain, the Laplace transform of x of t is x of s. The Laplace transform of y of t is y of s. Okay? And we call the transfer function g of s. The Laplace transform of g of t is g of s. So, which means the transfer function, again, this is an important terminology. The transfer function is defined as the Laplace transform of the output divided by the Laplace transform of the definition. A quick example we have done in the last hour. Okay, we have L times I over dt plus R times I equals the control voltage Vs of t. Okay, so suppose, let's assume the initial value is 0. So for t is bigger than or equal to 0. Okay? Now, if we take Laplace transform, we know we have L times S times Rs plus R times Rs equals to the Vs in S domain. So if I factor out the I of S, the Laplace transform of the curve, then we can determine the transfer function. The transfer function G of S is equal to the output. In this case, let's assume the output is the curve, and then divided by okay? So this is the transfer function. By using this technique, we can deal with many complicated structure of the systems, including feedback. Okay? So that's much more convenient to deal with, to find a solution, or to control the system. Okay? All right, now suppose we are given a system. How do we determine the stability? We know we have to find the poles, right? Okay, so let's go through some important. By the way, can I ask you to put this in the homework assignment? Then one more. This is very fundamental. Okay? And this one too. That'll be the sixth problem. This is very important, very fundamental, very basic in the momentum control. So you have 6 properties to prove in the homework assignment. Okay, now suppose we are given a transfer function. How do I determine the poles? And so let me go to the examples here. Okay, let's consider this simple system. What we are going to do is to find or to determine the time response of the output. Okay? So the corresponding function in the time domain are XLT and LT respectively. Suppose we are given the transfer function G of S is equal to 1 over S squared plus 3S plus 2. And initial value are all zeros. Okay? So we consider initial condition, zero initial conditions. Zero initial conditions. Okay? Alright. So let's assume the input Laplace transform X of S is 1 over S. Could you tell me again, what is the corresponding input X of T in the time domain? Come on. Yeah. Yeah, but there's a name for that. Unit step. Unit step function. 1, that's great, but we have a name for that. We call that unit step in automatic control, okay? Or in the signal system. Unit step. Yeah, U of T, right. Unit step, U of T, yes. So this is the unit step function. Okay? So what is the Y of T? So 1 of S first is equal to G of S times X of S. Right? Yep. Okay, please. So the Y of S is equal to G of S times X of S, the transfer function times the input, equals output. So the expression is very easy. So this is equal to 1 over S squared plus 3S plus 2 times 1 over S. Okay? Then the output, we have to take the inverse Laplace transform to obtain the output. So 1 of T, that is the inverse Laplace transform of the S. And that is equal to the inverse Laplace transform of 1 over S squared plus 3S plus 2 times S. Right? Okay? But what is the next step we are supposed to do? If we try to look at the table, suppose we have a table, Laplace transform table. So this is f of t, and this is Laplace transform of table. Okay, now if the input, if f of t is unit step, what is the Laplace transform of unit step? 1 over S, right? And let's start from impulse response, excuse me. What is Laplace transform impulse response? 1. Good. Okay, and then unit step. That's 1 over S. Right? Okay? And then what is the ramp? 1 over S squared. Good. Okay. What is the exponential function e to the negative of t? T is bigger than or equal to 0. Exponential function. 1 over S plus r. Right? Okay? And then So if we try to use table lookup, if we try to look up the solution from table, these are the functions. Okay, look at the function on the right-hand side of the table. These are the functions we can find, we can search, right? So there's an idea coming from the table. Can I, okay, let me say that. Let me stop for a few seconds. If I want to find the solution directly from this expression, can I find a solution from the table I have just listed here? No, I can't. I can't because those functions are quite simple. Only second order at most. Second degree. Second degree polynomial at most. Right? Okay, so for this simple reason, we have no idea how to find the solution directly by looking at the table. If I try to find the function that can match this transfer function, no hope. This is third order, third degree. Third order system, the polynomial is third degree. Okay? So which means what? Which suggests we have to break it down to smaller pieces, smaller or lower degrees. Okay? So the idea is very simple. Can I, or how can I break this down? Break it down, break it down, break it down. Okay, so how do I break this down? Some smaller transfer function with lower degree. Okay, so that's the basic idea. We want to break this down to some smaller systems with lower degrees. Okay, so mathematically what we can do is to use so-called partial fraction expansion. Partial fraction expansion. So we are going to break the transfer function down to some smaller systems with lower degrees. Okay, and mathematically we know that what we can do is to write it as the combination of three systems, A1 over S plus A2 over S plus 1 plus A3 over S plus 2. Why? Because the S squared plus 3S plus 2 is equal to S plus 1 times S plus 2. Okay? So I can rewrite the transfer function on the left-hand side as the sum of three smaller systems. Now, if I can find the coefficients A1, A2, and A3, then I will be able to find the corresponding time response from the table. Right? Okay? So that's the idea. Okay, and then how do I find the coefficient A1, A2, and A3? How do I find the coefficient A1, A2, and A3? There are many ways. Okay? You can expand the entire function. But then there's another simple one. To determine, say, A1. How do I determine A1? How do I determine A1? Now, if I can multiply the entire function by s. Oops, I should, yeah. Maybe I need to use space here, so let me write them here. I need a space. Okay, now if I multiply the entire equation by this, okay, and then let me take the limit. Let me take the limit. And then let this s approach 0. Approach 0, but not equal to 0, okay? Because if I let s be 0, there is a singularity here. That's a problem. We are going to have 0 divided by 0 is a singular term. Okay? So we simply let s approach 0, very close to 0, but not equal to 0. Okay? So this becomes the limit. Now I can cancel all of this to s. Did you see the trick? Did you see the trick? Now if I let s approach 0, then this term is, okay, a2 over s plus 1 is multiplied by s. And similarly, this a3 over s plus 2 is also multiplied by s. If I let s be a number very close to 0, this can disappear. This will disappear. Am I right? So what's left? There's only the A1 that we are looking for. Whoops. How wonderful. Okay? So what about the left side? We let s approach 0, the first two terms disappear. So we have 1 half equals to A1 right away. Okay? So now we have found A1. So now let's apply the similar technique for A2 and A3. Okay, so again, let's start on the cancel function times all of this. So any suggestion? How do I determine A2? Using a similar technique, right? So what should I do now?
Double s plus 1.
Double, no, multiply.
Double 1.
Okay? Yeah, good. Multiply both sides by s plus 1, right?
Use limit.
And take it, yes. And then take the limit. So this time the s is supposed to approach to
Minus 1.
negative minus 1. Okay? Why do I do this? This is because now I have A1 over s times s plus 1, and then A2. A2, okay? And then A3. Then A3 over S plus 2 times S plus 1. So what happens if I let S approach negative 1? You can see that this term disappears, right? Because S plus 1 approach 0. And likewise, this term disappears. So only A2 left. Okay? So, what's left? Now this is S plus 1, S plus 2, S plus 1. So these two now can be cancelled off. Okay? So that will be A2. And then this approach negative. So I have So I have 1 over negative 1 plus 2 times negative equals A2. So we have 1 negative equals A2. Okay? So now I found A2. And similarly, A3. So now we can determine A3 now. Okay. So this time I'm going to multiply the entire equation by S plus 2. So let S approach negative 2. Right? The same technique. So the right hand side now has only one term survived, one term left, which is A3. Okay? And what about the left hand side? So that's equal to the limit S approach negative 2, 1, S plus 2, and S times S plus 2. So this is equal to 1 over negative 2 plus 1. Or this is negative 1 plus 2. 1 half. Factor is 1 half. Okay, so now I found A3 as well. So now we have finished the searching of the coefficients A1, A2, and A3. Okay, so therefore, the two of us now can be written, the one of us, the two of us, one of us. Can be written the sum of the three smaller systems. Okay, A1 is 1 half times 1 over S and plus A2, which is negative, times 1 over plus 1. Then A3, which is 1 half, times 1 over S plus 2. And while t, the output response, the time response, the output, the time response is equal to the inverse Laplace transform of y dash. Now is the inverse Laplace transform of the three subsystems, smaller systems. So this is equal to 1/2 times the unit step function, which is 1. And then -1 times the exponential function e to the negative t, and then times unit step function. Okay? And then plus 1/2 times another exponential function e to the negative t times unit step function. Now, since we are considering the response for t is bigger than 0, okay? So while t is bigger than 0 equal to 0, we don't need to carry the unit step. So we can simply write it as 1/2 minus 1 times e to the negative t plus 1/2 e to the negative 2t for t greater than or equal to 0. So this is one way to determine the output, to determine the response in time domain. And a question one more time. Okay, now let me bring that 12 here over here. Okay. Again, if I let t approach a very quick number, these two functions will die out. These two exponential functions will die out, will approach 0, right? They will disappear when t is a big number. Okay? So we can divide this system, divide the output into two parts. One is the steady state. The other one is the transient. The steady state is the unit step, 1/2. Why is called steady state? Because no matter what the t is, this steady state is always equal to 1/2. When t approaches a very big number, these two terms disappear. What's left is only 1/2, this one, the steady state solution. The steady state solution, okay? And the transient response is the sum of these two terms. Why we call that transient? Because you can only observe these two terms in the beginning of the time response. When t approach to a bigger number, these two terms die out, these two terms disappear. So that's why they call this function the transient response. So this is, let me write on that. So this side, okay, this is the steady state. Steady state response. Okay? And then this is the transient response. transient response. Means they will die out, they will disappear when t approaches a big number. And so eventually you will not be able to see transient response. What you can see is only the steady state. The steady state. All right, up to this moment, any question? Okay, any questions from anyone? All right. If there's no question yet, let's consider another example. Okay, again, let's consider a linear system with a unit step input, and we are going to determine the output in a time domain. Now this time the transfer function G of S is 1 over S plus 2 squared. Okay, so we have double pole. So now we have double pole at negative 2 here. Okay, so what is the y of t? Okay, what is y of t? What is y of t? For convenience, let's consider zero initial condition. Zero initial condition. So the idea is to find any one integral, one of s first, which is 1 over s times s plus 2 squared, right? Okay? And then we are going to write it as a combination of some smaller subsystems, which is going to use a1 over s plus a2 and a3. Okay, here I believe that you have known this in high school. This will be s plus 2, and this will be s plus 2 triplet. I'm sorry, squared, not triplet, squared. We need a1 over s. We need a2 over s plus 2. And then we also need a3 over s plus 2 squared. So the question is how to write between a1, a2, and a3. Okay? So I think it's easy to determine A1 once we have done this. Well, even though it's risky up here. So we can apply the same technique to determine A1. Right? What about A2 and A3? Let me switch view. Okay. Yeah, that's fine. Sorry. That's fine. Okay, so to determine A1, let's multiply the entire equation by S, right? And then take the limit. So let S approach to 0. And then likewise, the right hand side we did the same thing. So when S approach 0, only A1 left. Only A1 left. Okay? So we have we have 1 over 2 squares. Yeah, 4. So A1 can be determined right away. What about A2 and A3? Well, I think time's up. I have to stop here. Okay, otherwise, some of you may have some other process. So please think about this. And then we are going to consider this case next time. Okay? So how do we find A2 and A3? That's very interesting. Okay? Okay, any questions before you leave? All right, and have a good weekend and see you next time. Maybe you can try. Maybe if you have something to go, yeah, just feel free. Okay? You have to go, then feel free. We can try this. Maybe you can see what happens. Okay, so to determine, for example, A2. So you may take that, let's take the limit. S approaches -2. This may be your initial entry, right? But what will happen? So the left side, you are going to have 1 over S times S plus 2 on the left hand side. Okay, and then the right hand side. This guy has A1 over S, it disappears, fine. But then we have A2 plus A3 over S plus 2. Did you see the problem? See that there's a problem here. What is the problem now? When S approaches infinity, I'm sorry, -2, the left hand side approaches infinity. Here we have 2 terms left. This is A2, fine. This is A3 over S plus 2. Again, when x approaches -2, this approaches what? Give me times A3. Okay? So we have a problem here. Think about this.